Hi class, we're going to take a look at section 7.6 today. Before we do, please take a look at this warm-up and pause the video. So hopefully you've had a chance to take a look at this warm-up, and it should be a pretty straightforward task based on our prior learning. But I'll run through it anyway just to refresh our memory quickly before we add on to this knowledge. It's going to set us up for today where we're going to be doing this and more with what we're going to look at today. So it's good review to activate our prior knowledge. Here we go. So we're going to be solving this eigenvalue problem over here. I'm going to be taking, I've already kind of set things up here. We're moving a little more quickly than usual here. I've already kind of set up the eigenvalue problem where I have R as our eigenvalue. And so we're doing the coefficient matrix minus like R times the identity. That's what that thing on the left is there. And so you'll remember that in order for that to be true, that the determinant of that matrix that appears here has to be 0 if this is really going to be true. And so now as we take that determinant, set it equal to 0, we get this characteristic equation that's quadratic, and we solve it. I'll just skate through the details here. You can, I'm sure you're capable of doing that on your own. And we should all get that for our values. Our eigenvalues. Okay, so now let's take a look at each one individually. So we got R1 equals 4, that's our first eigenvalue, and let's find the eigenvector that goes with that. The way we do that, remember, is to now actually go back up to this eigenvalue equation here and plug in 4, and when we do that here, we'll get this matrix, and it's just always true that we're going to get this kind of dependency between the rows, and the two rows are in this case going to give us the same information. If you take the first row and multiply row by column, this row times this column should give us this entry right here, 0. And if you want to do the second row times this column equals 0, you can do that too, but it won't give you any additional information about the relationship between C1 and C2. So we can see here that we have some freedom to pick a value for one of these two things. So you could just pick, let's say C1 is 1, and then C2 would depend on that, and it would have to be -1. So now we've got our eigenvalue eigenvector pair, the first eigenvalue eigenvector pair. Now let's also take a look at the second eigenvalue. We find the eigenvector for this in the same way. So hopefully you found what I did, and I've got a little bit of a hack here. Instead of doing like you could do like C1 is 1 here, and then C2 and then C2 would end up being 2/3, but I just kind of like the idea of, look at the form of the symmetry of that equation. Can you see that just by looking at it, that if you were to plug in a 3 here and a 2 here, that both sides would be 2 times 3, and the other side would be 3 times 2, like they'd be the same. So that's kind of a nice way to do it without actually doing like an algebra. Not that it's very much algebra, but regardless, we've got our eigenvalue eigenvector pairs that we need for this, and we can write down the solution, the general solution. This isn't an IVP, but if it were, we would have to apply the initial conditions also. Then it also asks us to comment on the asymptotic stability of the solution. So we notice now as t goes to infinity for this solution that the second part of this disappears, that the e to the negative t is going to disappear because that whole term will go to 0. And so we'll just get that left term, which will explode. So this is unstable. It's got like kind of a stable part, I guess you could say, but because of the one part exploding, it all explodes. And that'll happen if the eigenvalues are not both negative. In this case, since one is positive and one is negative, we would call it an unstable saddle point. Let's also take a look at the phase portrait. I've got it here on this page. And you can see that the phase portrait illustrates that too. So let me see if I can highlight this well for you. So along here, remember, I've got the solution here. 1, -1, in that direction, that's the blue one, right? Either in this direction or up in this direction. I've got some sample trajectories graphed here. You can see that if you head in that direction, you're headed away from the equilibrium. By the equilibrium, I mean the origin here in this phase portrait. And just to remind you, remember the phase portrait, by the phase portrait we mean this two-dimensional coordinate system where both the horizontal and vertical axis are the dependent variables in this system. So like maybe if it was an application problem, it might be the quantity of something, like the two populations, maybe two like biological populations. Or maybe it's two quantities, maybe it's two reactants in a chemical equation, or maybe it's two whatever, anything. So those two quantities are shown here, and it's not immediately apparent just by immediately looking at the portrait where t is. T, it's like the time axis. There is no time axis in this picture, but as time marches on, we're like moving along the arrows in the picture. Yeah. So as t increases, we just talked about this in the last slide. If you're in this area, you're going to be moving away. Along these lines here, this is the second eigenvalue we're looking at now. It's maybe a little hard to tell, but this is in the 3, 2 direction. So you kind of just think like you don't normally do with slope. That's a vector in the 3, 2 direction. So 3 to the right and 2 up. Or anywhere along that, scalar multiples of that. If you plug in t values, you'll get things along that trajectory as you go. You'll get closer and closer to 0. So I think that the phase portrait is helpful here. You could do it by hand to some extent. You could certainly draw those lines at least by hand. I think that should be something you should be able to think about. Now, whether you draw all of those arrows by hand is another story. You could do it just kind of tediously, but having a computer do it is very helpful. All right, today we're going to take a look at complex eigenvalues. So let's just proceed as we did before. Oh, sorry, let's skip this slide. I don't know why I have this in here. Okay, so when we are solving a system of differential equations with complex eigenvalues, we're going to proceed the same way that we did before, and then we'll see some difference along the way. So let's do it. In fact, right away you're like thinking, well, that looks just like the warm-up. So in fact, actually, let's do that. Why don't you take a second and pause and go as far as you can with this. Find the eigenvalues. You should even maybe be able to find the eigenvectors. Now, I warn you, because we're in this section, there might be an I somewhere in there involved, but don't let that scare you. Really, as we proceed here, so if you haven't done it, go ahead and pause the video and try it. But when you're ready, let's go through it. As we're going through it, you're going to see that you're going to get maybe a non-real eigenvalue, and that's okay. Let's just move through it and see what happens. So there's the system written as in vector matrix form, and we're going to do kind of what we normally do, just like the warm-up, set up this eigenvalue problem. We're going to be seeking the eigenvalues and eigenvector pairs for this system. So nothing to see here. Let's keep going. So we have this determinant. We're going to set it equal to 0. We get a quadratic characteristic equation again. Let's clean it up a little bit. I'm going to solve this by completing the square, just because it seems like it will yield nicely to that technique. And so I'm getting, for my two eigenvalues, 1 plus or minus 3i. And now we proceed to find the eigenvectors. Even though there's an I involved, really, it's not really a curveball for us yet. So in blue, we've got the first eigenvalue. And notice that I'm doing just like we did on the warm-up. I'm doing just filling that in to our equation, right? As I simplify that, we get this. Now, I had said before that there's going to be some kind of dependency in the rows. Is there a dependency between these rows? Think about it. Is there something you could multiply one row by to get the other? Are they scalar multiples of each other? And the answer is actually yes, they are. It's not maybe immediately apparent, but think about it and see if I'll let that be a little puzzle for you. Keep in mind that by a scalar multiple, we also might include non-real numbers, right? It is true that you can't just multiply some real number by one row to get the other. That is true. But think about it. So it is in fact the case that each row is going to end up here giving us really the same information. So we'll take the first row and multiply it by the column vector, C1, C2. That should end up equaling 0. Now let's clean that up just a little bit. And I'm going to use that same kind of little algebraic symmetry technique that I used before. How about for our eigenvector, we just use, look at this. If C1 was 2, and C2, if that was 1 plus I, wouldn't this just be kind of true? Kind of tautologically true. It's just kind of course that's going to be the case. So that's kind of a sneaky way to do it. If you want to be more, if you want to choose something else that works, that's fine, but I think that's kind of a slick way to instantly get our eigenvector. So we got in blue an eigenvalue eigenvector pair. Are we phased that there are like i's involved? Well, I don't know. It doesn't bother me if it doesn't bother you. So now let's proceed to do 1 minus 3i just to see what happens. Now feel free again to kind of fast forward, go ahead and figure it out yourself if you haven't already. I'm going to go through this quickly because it's pretty much the same kind of logic. And you'll notice that the eigenvector, the second eigenvector, has a very similar form to the first one. Yes, did you notice what the similarity is? They are in fact conjugate pairs. They're conjugates of each other, rather. So, and I want to make sure we're clear. Like 2, what's the complex conjugate of 2? It's 2. What's the complex conjugate of 1 plus I? It's 1 minus I. So this really is the complex conjugate of C2. It really is the complex conjugate of C1. And just as in chapters 3 and 4, we're going to seek vectors of real coefficients. Now you're going to see on the next slide that really we're only going to need one of these. So I'll just say right now, as a little preview for this, you're going to need to do this. You're going to need to kind of think through this and get their eigenvalue eigenvector pair. But in the case of non-real eigenvectors and eigenvalues, you are not actually going to need to do this second one over here. Or if you wanted to, you could, and you would just know instantly this is what it's going to be, right? You don't have to go through this work. This is not a coincidence. This always happens. So, in fact, like I said, we're only going to need one of them. We're going to use the first one that we found in blue. And you'll see why in a minute, why we only need one of them. There's like an argument we can make about linear independence here. And we're going to pull a very similar trick that we've done before with this part right here, this e to the 1 plus 3i times t. Remember how we resolved that? We used Euler's equation. Back when we were in chapter 3 doing second order differential equations, we did this. We're going to do it again right now. So as we do that, we can separate this into e to the t, of course. That's going to be that part. And then e to the 3i becomes cosine 3t plus I sine 3t by Euler's equation. So take a moment just to remember that's a thing we can do. I haven't even dealt with the 2 over 1 plus I part yet. But now I'm going to start kind of trying to see what we've got here and clean it up. I'm going to start by pulling out the e to the t, since I don't need that. And the goal right now is I'm going to try to be, in the next couple lines of work, I'm going to be trying to collect things that have an I and things that don't have an I. So notice I've already started, I'm just multiplying this out here a little bit. And then, okay, I've done it. Okay, so take a moment, pause the video, and make sure that I really did separate things that have an I over here and things that don't have an I. So notice that I've factored out the I out of all these things. So we've got this part right here is going to be 2 sine 3t, and the I put out in front. And then the things that have an I down here, these two items, these two terms, are going to appear here, and if you were to multiply the I back in, you would get that. Okay, so just verify that this equals really belongs here. Is that right? Yeah, that is the same thing, but now we can really see we've got like the things that don't have an I, and then I times the imaginary part. Okay, and then here comes the claim, and it's a very similar claim that we made back in chapter 3 when we did the same kind of thing. I claim now we have two linearly independent solutions here. This part and this part. And that forms a fundamental set. And so we're going to put a C1 in there and C2, and that'll be we've got our linear independence that we need for two solutions. Yeah, and that's going to be a theme throughout the rest of mathematics too, is that like non-real numbers, complex numbers, when you have like a non-real part, a pure imaginary part, and a pure real part, they're like kind of in the complex plane, they're orthogonal to each other, right? And so it makes sense that they span some kind of a vector space. And so that there's that linear independence that you need. So that's just kind of giving you a little intuition. There could be a lot more said there, but to be fair and to be clear, there's not like, oh, well, there's some kind of shady things going on, and these are kind of not, there might be non-real components of these or something. No. Everything in this box is real valued. And so this I, as we move from here to here, this C2 would incorporate it could have incorporated a non-real component so that we get this, but ultimately C2 can be real. And if you use like initial values, you can see that that's the case. Let's talk, for this particular problem, let's talk about its stability now too. It's a little strange now. If we think back to the warm-up, we're used to, with the real eigenvalues that are distinct, we're used to kind of having two lines that we saw. That's kind of classic, and we understand that. We have lines and we have arrows on those lines, and we were headed toward 0 or not headed toward 0, right? So let's think about that here. We don't have really, like if you were to go to plot those vectors, no longer are our vectors, what were our eigenvectors? It was like 2 was the first component, and 1 plus 3i was the second component. Well, there's no sense in which we're going to like draw that as a vector per se in the portrait, face portrait. That doesn't really belong there. You don't have like an arrow, so the complex eigenvectors don't show up in the way that normal eigenvectors do, real eigenvectors. Here's how they show up. We kind of maybe expect that this might happen. Think about it. Complex numbers have meant for us a long time now rotation of some kind. And notice the phase portrait. I'll have the computer sketch it for us. Take a look. This is the phase portrait for this system that we've just solved. What do you notice? Do you see any kind of rotational aspect in this phase portrait? Let's sketch a few trajectories now. Here's one, for example. And notice the direction of the arrows. Could you have predicted the direction of the arrows? Which way are they going? You get this kind of spiral trajectory in phase portrait when you have these cosines and sines involved, don't you? Which direction are the arrows going? They're pointed kind of away. If you're making a prediction right now and you're thinking, Mr. Chase, I think this is an unstable equilibrium, you would be right. Yeah, they're all kind of headed away from the origin in a spirally way. Here's some more trajectories. And this is called a spiral center, and it's asymptotically unstable. And notice the reason why is because, these are all kind of bounded things in terms of t. All of this stuff is bounded. It never gets any bigger or smaller than a certain number. But this e to the t term, which remember where that comes from, it's that the fact that that coefficient on t in these exponents is 1, like a positive 1. Remember that came from the fact that that was the real part of our eigenvalue. Our eigenvalue was 1, and the imaginary part was 3i, or negative 3i, right? So let's just pause as we finish this lesson to consider where we are. At the close of our last lesson, we had kind of built out this set of phase portraits that we were familiar with, these kinds of equilibrium, these kind of equilibria. So take a look at these. So the first one is where both eigenvalues are positive, and so we get this kind of headed away, definitely unstable. Both being negative, we have a stable equilibrium because things are kind of headed towards 0. Again, you could kind of imagine these in the same way we did with like vector fields. If you were like to drop a little particle into these, it would kind of head toward the center. If it was near the center, it would head toward the center. We can't be sure of that on the unstable node. If you put a point at 0 precisely on an unstable equilibrium, remember it will stay there. But if you were to nudge it even just a tiny bit, it's going to go zooming off. And the same thing is true for the other one, the unstable saddle. That's the one we had in the warm-up too. Okay, now let's talk about complex ones. Now we have this unstable spiral center. That's the one we just talked about. And that is when we have non-real eigenvalues, and the real part is positive. That's what we just saw. Here's the other situation which you could probably predict. If the real value, the real part of our eigenvalue is negative, then we're going to have a spiral center. If it's a non-real eigenvalue and it has a negative real part, we're going to be spiraling, and we're going to be spiraling in. Now, what's the last thing that could happen? Did you think about this? Well, what would happen? Could you not spiral in or out somehow? And the answer is yes. How does that happen? Before I reveal it, can you make a guess? If you said that we need the real part to be purely to be 0, so we have just an imaginary, that would be that like e to the t part, right? E or e to the negative t. Those are going to send us in or out. But if that e to the part is just e to the 0, then e to the 0 is 1, and so the only contributing factor is we're going to have kind of just those periodic parts. So we're going to get some kind of elliptical patterns. So we're going to consider that stable, because you're not going anywhere. You're not headed out. You're not flying out. You're going to be in a stable pattern, and you're not going anywhere. It's a little beyond what I want to say right now, but there's a lot of kind of good applications to this and tie-ins with things we've already even learned this year. So one of those is our harmonic oscillator, and this is making me think of that right now, right? So you'll find like one representation you can give for a harmonic oscillator is a phase portrait like this. And the way you do it is by converting, you could convert a harmonic oscillator to, instead of a second order differential equation, remember that's when we learned about harmonic oscillators, it was back in chapter 3. And instead of doing a second order differential equation, remember from our first day of this unit, you can turn every second order differential equation into a system of 2 linear differential equations. And that's what you can kind of be seeing here. If you do that, what you'll get is, if you take a harmonic oscillator second order equation and turn it into a system of 2 linear equations, you'll get pictures like this. If you have in your harmonic oscillator a damping term, then this is what you'll get. It's kind of in our time space, right? It was that like wave that went slowly, like kind of wiggled down to 0, right? That's kind of what this is. That's the equivalent of that here. It's kind of headed into 0. And this is kind of the picture of a harmonic oscillator in a phase portrait. It doesn't have any damping. It's the spring that's going up and down, unrealistically, forever, right? So it's kind of orbiting in this picture. And that, I think, brings us to the end of our lesson today. Obviously, you'll want to check out the slides, go into more detail on this stuff, work out some of these examples for yourself, and if you need some more resources, they're, of course, here linked at the end. Thank you guys for your attention.